Study the change in the optimal value of the objective function when there is changes in the amount of resource available. Okay, so in the carpenter's problem, whatever the resources, one resource was the material itself, that was the lumber, and another resource was the labor. Okay, so this corresponding to these two resources, what were the some of the restrictions were there, so corresponding to this we got one constant, and corresponding to this we got another constant. Okay, so what here we are taking a specific example ki there are 120 units of labor available currently. That means whatever the problem we have solved in the last chapter, there were 120 units of labor available. Okay, all of which were used to produce the 12 tables and 15 bookcases. 12 tables and 15 bookcases means as the maxima was occurring at 12-15, so obviously the optimal solution, that is the optimal profit, was occurring when the carpenter was making 12 tables and 15 bookcases. Okay, so now the question is, what is the effect of increasing the amount of labor? So 120 units of labor was there, and what was the labor constant? If you recall back, this was the labor constant 5x1 plus 4x2, that was less than equal to 120, less than equal to, because either it was to be used or was to be kept in the for future use. Okay, so 5x1 plus 4x2 was there, but now what change we are making? B2 represents the units of available labor it is at present. That means for our problem we are considering ki 120 is replaced by B2. Okay, so now what is the constant becoming? 5x1 plus 4x2 less than equal to B2. Okay, so what happens geometrically as we vary B2? So B2 is now becoming a parameter. I have not given any fixed value. Obviously B2 is going to vary over the parameter range. Okay, so answer this question, graph the constant set for carpenter's problem with the original value of B2 equals to 120 and a second value. So what actually we are trying to do here, we are trying to compare the different, or rather study the different effects for changing this constant. So 5x1 plus 4x2 was there, less than equal to 120 was there. Now we are changing that 120. Either we can decrease the 120 or increase the 120. Okay, so let us see what happens here. Okay, so this was the original, say suppose this was the 5x1 plus 4x2 equal to 120. This was the original constant. This line was the original constant. Okay, now what we can do, this line can be shifted, as here they are shifting here like this. Let me just draw a figure in rough. This was the original line. Okay, and now what we are doing, we are shifting it. Okay, so that is what one example of it is here, this one. Okay, the value of this is changed from 120 to 200 suppose. Okay, and what we know ki there was another constant. What was that? The material constant, that is the lumber constant. So the lumber constant actually is coming along this straight line, this one. This is the lumber constant. Okay, so the lumber constant is remaining the same, the invariant it is remaining. So okay, so now when we are changing this labor constant, obviously if I now want to solve the problem, suppose we want to solve the problem with this one, then what we have to do, again the same strategy, we have to find out the feasible solution. If it exists, then we have to find out the extremal points, and then at all the extremal points we want to find out the optimal value, the value of the profit function, and of all those profit function which is maximum, that will be coming. So the main thing here in this strategy is that the feasible solution must be there. So it is not like that ki this constant, that is labor constant, suppose the labor amount, that is the labor available to the carpenter, is enormous, is huge. He can vary to a large extent. Okay, from 120 to any value, almost any real value, 10,000 to 20,000 he can take. But that will not solve his problem, that will not maximize his profit, because he has to respect, or he has to abide by, or he has to follow the other lumber constant also. So he may have a huge amount of labor with him, but all those labor will not be useful to maximize his profit for this sum. In that case, the lumber constant has to increase simultaneously. So that is why this is the physical meaning, the practical meaning is this. And algebraically or geometrically, what we mean, we want to find out the feasible region. That there should be the feasible region. From there only, the boundary of the feasible region will give one extreme point which will maximize his profit. Okay, so this profit cannot be arbitrarily maximized. So that thing you now see in the picture, ki this is the lumber constant, so it remaining invariant. What will happen if I go on shifting my line? So this was the original one. Okay, and this was I was going on increasing the labor. Okay, then at a time what will happen? At a time, so suppose, let me just draw this other constant, the lumber constant, right? So lumber constant, let be like this. Okay, so what is happening, if we go on increasing this labor infinitely, at a time will come when there will be no intersection of this one with this. So if there is no intersection, that means what? there is no feasible region we are getting. So that means what, if I say ki, okay, my labor is this, okay, so no problem, you can take the labor like this. And if you just recall back, how did we derive it? The labor was, for example, if the labor I am taking a large amount, so suppose this one was the original one and I am taking it increased as this one. So if I take this increase as this one, then what will happen, this will be less than equal to this, so this will be coming because of this constant. And another one is the lumbar constant. So the lumbar constant, let me be like this, okay. So for the lumbar constant, this one is coming. So again, what is the main thing, this intersection region, that means only this portion can be coming, okay. So earlier what was it, earlier it was like this, because that is the main problem which was given to us. It was like this portion was the optimal portion, but here it has increased up to this one, but not more than that. So the increment is just restricted by the, say, first this constant also, the lumbar constant also. So that is what you see when I am going on shifting this line, the intersection I have to keep in mind. There is the intersection of this line with of this constant with the other constant. So here if I go on increasing this line, shifting this line, this is intersecting, acha, this is also intersecting, but see, this one is going out of the intersection, it's impossible, okay. So as it is not intersecting, it won't give you anything extra, because the maximum extremum point will be in that case this one. So in that case, if this one is the maximum extremum point, that will give you the optimal value Z max, okay. So what we understood from here, ki if I change the resource, labor is a resource, so if I change a resource, obviously I am taking the better option, ki if I am getting more and more resource, more and more labor, my profit function cannot increase arbitrarily. The other constant will put a restriction over it, okay. And so obviously there will be a change in the optimal function, so we will now study the change. As it is not arbitrary, so obviously there is some particular change with the change in the resource of labor as we are considering here, okay. So now let us see how is the objective function value changing, okay. So that is what they have just said here, okay. I am not going into this again, that the whatever problem I said of this, it is explained here. From A it is moving to A dash, as you can see from here, okay. So initially for the problem which we have solved, this was a maxima, but here the maxima is shifting from A to A dashed, okay. If you calculate, Z max will be, that is Z will be maximum at A dashed, Z A dash will be the maximum value, that is the maximum profit, okay. But beyond that, if you go on increasing, at a time will come after 34.5 here as it is shown, there will be no intersection of this constant 1 with constant 2, that is lumbar constant and labor constant, there will be no intersection. So in that case, that won't give you anything extra for the optimal function as far as our strategy is concerned, okay. So now whatever this objective function is increasing, let us now see how it is changing with this increment in the labor resource, okay. So this part I am now skipping. Now this one, acha. Now however, if that B2 is increases beyond this one, the optimal solution remains at the extremal point, as I said, 34.50. This is the last one which is coming, okay. The lumbar mass constant must also be increased if the objective function is to be increased further. That is what I said, okay. And thus, increasing the labor constant to 200 units results in some excess labor that cannot be used unless the amount of lumbar is increased beyond this present value of 690. So for the problem which we solved, the lumbar constant present resource available with respect to lumbar was 690, okay. So that is what, as I said, ki if you are further want to increase this 690 thing, lumbar constant of 690 resource should be increased. Otherwise what, you can take this labor to be 200, okay. You can take this labor to be say 200, but this 200 amount of labor will not be used. A part of it will be there for future use, okay. Acha. So this is done. Then following a similar analysis, the B2 is decreased, the value of the objective function moves along the lumbar constant until the extreme point 0,23 is reached. So now the next thing, suppose if the carpenter is getting less amount of labor, then what, obviously his profit will decrease, but that will also be limited. His profit cannot decrease arbitrarily, okay. So there also lies this thing, and the ultimate one is coming here. In that case, optimal value is given for this 0,23. So that means in that case, by making 23 book cases, he will make the maximum profit. In case his labor is decreasing, okay, ultimately his labor is going on decreasing, so ultimately it should lie along this one, like this, okay. So now with this one done, then further reductions in B2 would cause the optimal solution to move from 0 to 3 down the y-axis at the origin. Okay, if we move on further, then ultimately we will get no feasible solution. No feasible solution. If you just go on moving like this and this and this, ultimately origin will be there. No feasible solution is there. No region is coming, then it will not be done like that. Okay, acha. Now let us see with this what they are saying. Let's study the change. So now let's find the range of values of B2 for which the optimal solution moves along the lumbar constant as the amount of labor varies. So this is one strategy we are fixing to learn, or to rather analyze the change in the objective function's value with respect to the amount of labor varying. Okay, and with reference to this figure, we can convince ourselves that we wish to find the value for B2 for which the labor constant would intersect the lumbar constant of the x1 axis. Okay, or point E. Okay, so at point E, the amount of labor is this much. Okay, similarly, we wish to find the value of B2 at a point D, which is this one. Okay, summarizing, as B2 changes, the optimal solution moves along the lumbar constant as long as this thing. So what actually we are doing here? We are finding out the extremum cases, the ultimate cases, not the extremum value I am meaning here, the ultimate cases we are seeing. So what is the ultimate case I am seeing? At this point, as you can see here, the two extremum cases are considering to be the point D and the point E. The point D, when I am moving this B2 inside, that means when I am going on decreasing the labor, this is the point D which can come at maximum. Okay, and the point E is going to come whenever I am going on increasing the labor. So increasing the labor will give you this, and decreasing the labor will give you this line. Okay, so in each case it has to just be compatible with the lumbar constant. Okay, so for that compatibility idea, or that for compatibility requirement, D is coming to be the extreme point if I go on decreasing the labor, and E is coming to be the extreme point when I am going on increasing the labor. Okay, so that means what? That is putting a restriction over ultimately what? The parameter B2, because B2 is the variable. As I am varying B2, that's why this can be happening ki you are going on increasing the labor or you are going on decreasing the labor. That means you are going on increasing B2 or you are going on decreasing B2. So that gets restricted now. How is the restriction coming? With respect to the extremal point, the restriction is coming, because for at the extremal point, what is the maximum amount of labor possible? It is 5x1 plus 4x2 is the main idea. So at 34.5, 0, 5 into 34.5 plus 0, so 4 into 0, so this is the labor. Okay, so the main formula we are using is the constant which was given 5x1 plus 4x2. So at E we are calculating it, that is giving us this one, and again at D we are calculating it, this one, which is giving us this one. So at D this is the amount 92, and at E this is the amount 172.5. So B2 variation can be, and or rather is restricted by 92 and 172.5. Nothing else can happen in this case. Otherwise you won't get any feasible region. Okay. Acha. So with this one, however, by how much? Now the next part of the question, ki once I have given some boundary over this parameter, unknown parameter B2, now let us see how the objective function value is changing. Let us study with the change or the variation. If B2 goes on varying from 92 up to 172.5, what will be the effect on the objective function's value? Okay. However, by how much does objective function change as B2 increases by 1 unit within the range 92 to 172.5? That means by 1 unit it is increasing. Okay. So here we are analyzing it in two ways. First, suppose of the B2 equals to 172.5. The optimal value is then the new extreme point, this one. Obviously, if I take B2 to be 172.5, then that means what? 5x1 plus 4x2 equals to 172.5. But what is 172.5? Which is the intersection of the lumbar constant and the new labor constant. Okay. So now you can see it is becoming, this E is becoming an extreme point of the feasible region. What is the feasible region now? Let me name it as O, E, and say S, O, OESO. This is the feasible region now. Not OESO but OEDO, this one. Okay, so this is your extremal point in that case. So what is the objective function value? Z at the point E is the objective function value. So that is what they are calculating here. Okay, and the value of the objective function turns out to be this one, because what was the objective function? 25x1 we just did in the last one, 25x1 plus 30x2 equal to Z. Okay, so this one was there. So z equals to 25x1 plus 30x2. So at E, what is becoming? E is becoming 32.5. It is becoming 0. So it is calculated to be 862.5. Thus the objective function is increased by what amount? It was originally 750. It has increased to 862.5. Okay. So 112.5 units is the increment. When it is this increment is coming? Whenever you are increasing your B2 from 120 to 172.5. Okay. That means here we are getting a ratio in case you may say. Okay. How is the ratio coming? Here, once you are taking the increment in B2 and the corresponding increment in Z, okay, so here increment is in B2 is given by how much? 120 and 172.5 difference, so 52.5, right? And what is the corresponding change in Z? It is 112.5. So you now just study. What I am going to study? The rate of change of Z with respect to B2. That means with 1 unit change in B2, what is the change in Z? So the ratio should be Z change. Say I say it better to say del Z and del B2 because it is a change we are denoting. So del Z by del B2. Okay, so this is this one, which is becoming 2.14. So per unit change of B2 is producing a change of 2.14 unit profit of the carpenter's maximum profit. Okay, the main thing is maximum profit of the carpenter. Okay, now let us analyze. That means now let us follow the second strategy. Here we said we will analyze in two ways, or let us consider another one. What we did here, we just considered the present value and the extreme value. That is the present case, that is the present amount of resource of labor, and the extreme amount of resource of labor which can be possible up to considering the feasible region, that is up to considering the solving this maximization problem, that is up to considering being compatible with the Lombard constraint. It was this E, that is 34.5 at the point 34.5, okay. So we took the present one and we took the extreme one, but we could have done in a separate way also. We could have taken the present one and just 1 unit we would have increased. That means we could have started from 120 and increased by 1 unit, means it becomes 121. We can also do like this. Okay, so in that case, if we do it 121, then what is the new line you are getting for the labor constraint? It is 5x1 plus 4x2 equal to 121. So 5x1 plus 4x2 equals to 121. So that is what. So suppose this was original 192 and I am not 92, 120 suppose, and now I am getting something more than that, so 121. Okay, so with that what we will get? We can get another extreme point here. Okay, actually this figure is not shown here. Let me just go into the other figure. Okay, so this one 5x1 plus 4x2 121 if I say. Okay, so this one, suppose I am just you can just consider it separately. Let me just consider it separately, it's better. So this is my Lombard constraint. Okay, and now say this is your original labor constraint 120, and then the labor constraint is increasing and becoming say this one. So this is the new thing, A dashed, and this was the original A 1215. Okay, so this was A dashed. What I have to do? I have to solve the two constants. What are the two constants? One is the Lombard constant, which is given by this Lombard constant here is given by which one? Whatever, 5x1 plus 4x2 and this one. So let me just see here. This one 20x1 plus 30x2 equal to 690. This is the Lombard constant, and your new labor constant 5x1 plus 4x2 equal to, instead of 120 it is 121. So you can solve it to find out what the extreme point, because it will correspond to one of the extreme point of the feasible region boundary. Okay, so that is given by this. If you solve it, you will get A dashed 12.429 comma 4.714. Okay, so if you now calculate the value of Z at the point A dashed, it will come out to be 752.14. Okay, so here also if you just recall back, what was the original value of the objective function maximum value? 750 was coming in our original problem, but here it has increased. See, if he has more labor, quite obviously he can use it. So the increment has occurred per unit change in the labor amount, increase in the labor amount. It is 2.14 is the increment which is coming, because I have increased only by 1 unit, from 120 to 121 I have increased. So corresponding to that, the increment in the Z maximum value, that is maximum value of the profit function, is 2.14. So here this is the net change which is occurring. So you see here, if we study like this net change is 2.14 here. Here also you are getting 2.14. So we are just following the separate strategies, but obviously we are going to get the same result in that case. Okay. So this is the way how we analyzed here. If we change the labor resource, then how there will be change in the optimal value of the profit. Okay. Obviously the optimal value of the profit will increase. Similarly, one could have taken the decrease also from 120 to 119 also you could have taken. Okay, then in that case what you have to solve? You have to solve this 20x1 plus 30x2 690, because lumbar constant remaining is fixed, but in that case 5x1 plus 4x2 is also 119. You have to find out the extremal value, point of intersection, and find out your Z optimal. Obviously you will see that will be less than 750. Obviously the carpenter is decreasing the labor amount, so obviously his profit is going to decrease, his profit is going to be hampered. Okay, that's what is occurring there in case you decrease the labor amount. Okay, and again the whole analysis which we have done so far can be considered with the lumbar constant also, or can be keeping the labor constant fixed, or can be considered varying both the lumbar constant and the labor constant. Okay, so now you get the idea, just a rough idea we are just going to give here. You can get the idea ki how if I change these constants, or in the previous video which we just explained ki if you change one of the coefficients of the objective function, how it is going to affect your objective function's optimal value. But in that case, every time I am saying there should be some fixed parameters or fixed conditions. That means which is not going to change. Obviously, if you are going to just change the problem, or if you are going to resolve the problem in one case, or if you just want to modify the problem in one case, not all the constants, not all the parameters are going to change simultaneously. Of course, some will be there which will remain fixed. Okay, so whenever we are trying to make the sensitivity analysis, how much sensitive our solution is with respect to the changes we are making, obviously first and foremost of all we have to segregate ki okay, these are the invariants with respect to the problem which we are changing. Okay, for example, in here the invariant was the lumbar constant, it was never changing, and also the invariant was the profit per unit table, the profit per unit bookcase of the carpenter, because the objective function I am not also changing. 25x1 plus 30x2 is the objective function, was the original problem also. Here also we are keeping the same thing, we are not changing it. So the profit that the carpenter is making per unit table or per unit bookcase, he is not changing that. Okay, so that is remaining constant, lumbar constant remaining constant. Okay, only the labor resource is changing. Okay, in the previous last video what we did, the constant was not changing. The constants were not changing means what? The cost per unit labor, or the cost per the amount, the labor amount required for bookshelf or per table was not changing. The lumbar amount required per bookshelf or per your table is not changing, and the whole resource available is not changing. Okay, so all the constants remaining fixed. What is only changing? The objective function changing. How the objective function is changing? The profit per unit table is changing there, or you may change the profit per unit bookcase also. Okay, so all these things, in that case we have to keep that one in mind, and all these remaining constants. So all these remaining constants, that's why the constants were the same. Okay, we only just now once we kept the extreme value at the same point as before, is 1215, and otherwise it was, if it was changing, it was putting some restriction over the parameter C1 there. Okay, so this is how we study one of the two methods of it. Just a very few instances we have considered here for studying analysis. It can be done in many ways. Okay, so let us stop here.